Okay, so my great pleasure to introduce our speaker for today. Sebastian Lehnhoff is a full professor of energy informatics at the University of Oldenburg in Germany. He got his doctorate at Dortmund in 2009. He's the chairman of the board of the OFFIS Institute for Information Technology. And he's got a lot of other credentials that I'm not going to go through. But the one that is most important is he's been really active in the SIGEnergy, which is where I met him within the ACM Special Interest Group on Energy. And he's been responsible for organizing many conferences. And in fact, will be helping to organize the E-Energy conference in Rotterdam next June that some of us will be going to. He's going to talk to us today about smart grid trust assessment. So thanks so much, Sebastian. I'm sorry you couldn't come here in person, but we're looking forward to your talk. So it's all yours. Thank you.
Keshav, thank you. Can you hear me well?
Yes, we can hear you very well. Thank you.
Okay. Last piece of information. What is the precise time I should stop? Okay.
We have another group coming in here at 1:55 our time, so in about 50 minutes. So if you could end by in about 45 minutes or so, that would be great. Thank
awesome.
you.
Okay. Yeah, thank you for having me. Virtually, I'm having a cough drop in my mouth, so hopefully I'm not mumbling too much. Yeah, smart grid trust assessment. I come to that in a second. I have a professorship in energy informatics. So typically I'd like to start with saying a few things about energy informatics. And I know that Astrid Niese has been given a presentation in your group as well. And I know she will also probably or likely will have said something about cyber physical energy systems, energy informatics. But still, I think one cannot say enough of it. So why energy informatics? Energy informatics is basically a term that we came up with here, probably in parallel with other research groups, deriving it basically from the term cyber physical systems. And cyber physical systems, if you are familiar with them, is basically a term reflecting that everything started in that direction with embedded systems becoming interconnected, embedded systems controlling typically electric magnetical processes. And due to the interconnecting of these embedded systems with these specific, typically real world actuators, modeling algorithmically wise, that was pretty much a new area, and new methods, new models, and so on needed to be developed. And looking from an energy perspective, one could say that an energy system is a very it could be a cyber physical system, but with special characteristics. And the special characteristics are basically the 5 that I have here. It's a safety critical infrastructure. So energy systems are critical. If they fail, we have severe issues. Worst case, human lives are at risk. They are really, really large. So this is a sky view of the European intercontinental energy system, and it spans from the northern part of Denmark to the southwestern part of France, eastern part, Bosporus, Turkey, and so on. So it's actually continental spanning, and it's actually second only to the internet. If you're looking for a larger infrastructure, an interconnected infrastructure, then you end up with the internet. The second largest is already the energy system. And what it really sets, or what really sets it apart from the internet is basically the propagation speed of phenomena. We're talking about events, faults, failures, things that get propagated basically with the speed of the electromagnetic wave through the medium copper, super fast. I have an echo here. And that is obviously a problem. You cannot really react to something that fast. So what you have to do is you have to plan accordingly. You have to deal with eventual outages, failures, resilience then becomes a topic, but that's pretty unique. And of course, in a safety critical system, that's a specific challenge that you need to address. We have a specific market perspective. These systems have been developed over 100 years ago, vertically integrated, but nowadays, due to increased competition, basically the provisioning of energy on different time intervals, levels, and so on is market-based. And that's also a specific challenge because we see these shortages on energy markets all the time, and having a shortage on an energy market is eventually threatening the safety of that critical system. And we can see this actually all the time. There was a famous incident over 2 decades ago, Enron in the US, but we see this as late as earlier this year on the European energy system, where suddenly clocks began to lag due to energy shortages and basically under frequencies in the energy system. And if that is not enough, basically with this increased competition, we actually see a lot of conflicts of objectives, omnipresent, maybe not as threatening and as wide as this image implies, but basically every consumer tries to get a lower price, every producer tries to get a higher price. I mean, that's kind of obvious, but we see system operators having the prime objective of keeping the power quality, where market operators having different objectives. They are not necessarily directly orthogonal to each other, but they have different directions. And again, in a safety critical system, that may be problematic. And that in its entirety is actually justification for treating these energy systems as specific cyber physical systems with unique challenges in terms of modeling, optimization, and so on and so forth. And that is basically why we by now have a group of roughly 100 people, 5 professorships only dedicated to this energy informatics, so modeling, optimizing, controlling the energy system. Yeah, and what we're doing basically open heart surgery on that system. Given everything that I've just told you, that's, well, that's at least brave. But of course, we are converting this energy system. We have the energy transition as a mega challenge for us, for our society. We are substituting many larger generators for small scale devices, PV, wind, CHPs, and all these kinds of devices, introducing even more competition along the way. And of course, we couple sectors with that originally more or less isolated system that introduce a plethora of interconnections and interdependencies. We connect the heat sector, the gas sector, and of course, we network everything through digitalization and, for example, also introduce loops in terms of information flows, which is pretty interesting in terms of modeling. We also, on a more technically or technology-oriented perspective, introduce many new technologies that are very different in terms of maturity when we compare them to classic primary technologies like transformers and stuff like that, which are there and typically remain there for multiple decades. We are introducing IoT, AI, data, big data technologies, data integration, data-driven methods on, again, procuring specific resources there, with the typical exception and expectation from that domain that we need to update them, that we have some uncertainties regarding the goodness of these methods and so on. And that's pretty much paradigm shift on its own in the energy system. Let's move a bit more to the topic of and the focus of this presentation. What we also see is we introduce a lot of new effects. I already mentioned interdependencies between those sectors. And since we have firstly interconnected different sectors and levels in that system, we might see specific or encounter specific phenomena for the first time. So we have these strange new phenomena that we need to detect. We also introducing a lot of classic IT errors or issues that we have not yet seen in the energy system, that we basically have learned to live with in IT systems. For example, updating regularly our systems is something that's fairly new to IT in energy systems. The best example is, for example, protection systems. Protection systems run their own OS. Typically, it's a full-fledged embedded system. It's a computer on its own, sometimes even running something like Windows 3.11. It's installed, has been installed there 30 years ago, and has never been updated because an update procedure does not exist for these kinds of edge devices, which is kind of interesting and leads to a couple of follow-up questions if you think about this. And of course, along that line, we see a lot of sophisticated cyber attacks in these areas because they're very valuable targets. They're very interested to state actors, and we unfortunately encounter these kinds of things. Looking at the different levels and the different parts of the system where you can now see these kinds of technologies being implemented and being rolled out. This is a very abstract figure. I'm not going into detail of everything, but on the, I have a pointer. Here in that part, you typically have this control room, the SCADA system, the supervisory control and data acquisition, where you typically aggregate a lot of data to do forecasting, to calculate the network loading, to forecast the network loading, and on that level, try to detect anomalies and, for example, then identify topology switches, redispatch of power plants and stuff like that. Going more downstream, you have the processes connected to more individual or smaller groups of devices. You see the monitoring of rural streets, rural areas, quarters, single devices, single battery storage systems, so monitoring of operating states, and somehow locally assessing the closeness to specific feasibility margins. So for example, the closer you get to a voltage margin, the more critical the situation may be assessed. And in Europe, we have something like a traffic light concept. So if devices or group of devices is moving towards a specific boundary condition, the traffic light goes to yellow, eventually goes to red. And depending on the phase you're in, you can try to mitigate with different ways. Red obviously requiring real-time interaction or interruption of this situation. And on the other side, you see a lot of market-related algorithms and so on and so forth. I'm not going into detail here. But along the notion of this presentation, what we can also see here and what we also get a wide range of entry points into the safety critical infrastructure. Of course, the overall narrative here is a bit cybersecurity, but must not be. We see this entry points for classic IT issues, software bugs and these kinds of things, basically on all levels. And even interconnecting different levels that have been hitherto not connected. That said, looking at this famous quote by John T. Chambers, former CEO of Cisco, that you only have two types of companies, those that have been hacked and those that don't know that they have been hacked yet, is then a motivation for some parts of our work, basically looking at the anomaly detection and the assessment or estimation of the states and the criticality of the states given the amount of information that is actually available. And it's good to start very roughly on the classical kinds of systems that are available for that purpose in energy systems. And one or the initial step would be to actually try to systemize, categorize the vectors that are of interest here. Again, super broad, super abstract. IT/OT hacking, for example, with the idea to actually remotely access and control such an infrastructure. It's a very famous hacking incident almost 15 years ago in Ukraine, where Russia remotely controlled and shut down parts of the Ukrainian power system. Data spoofing is then something along the lines of data injection, trying to spoofing some situations to have the overlying supervisory control, maybe overseeing specific phenomena or even taking wrong actions against something that is not actually taking place. We have data manipulation, and even something like excitation of dynamic instability, sliding modes, for example. If you Google these kinds of things on IEEE Explorer, you find many papers on that topic, basically stepwise manuals, if you want, for classic grids to actually execute these kinds of things, because it's actually really easy to implement these kinds of data manipulation in energy systems. The only reason we don't see them that often is that basically simply hacking a bad password is so much easier these days in these industrial environments. There are some systems in place actually to detect these kinds of things. We have classic intrusion anomaly detection that try to identify abnormal network traffic. They are typically trained based on normal behavior with, of course, the challenge to get that normal behavior. Typically, you just define historic recordings of your network traffic as normal without ever being able to be really sure that there was not really any abnormal traffic in there. Or you have something classic state estimation where you collect everything, all measurement points in your system, and calculate a consistent system model or system state out of that. Typically, that requires overestimation, so you collect a lot more data than actually the unknowns in your physical or mathematical model that you want to determine. And then behind is basically an optimization routine that tries to minimize the error by fitting and mapping these measurements to the model that you actually try to estimate. It's known that these systems are important. You need to have them. It's sometimes even legally obligatory to install them, but they're by no means enough to actually detect critical situations in digitalized energy systems, because they're typically, bottom line, it's a key takeaway message here, they typically are based on normal behavior that you determine at one point. And since we are moving and steering the system, basically in uncharted waters here, we are connecting everything. The system is going to behave differently from how it behaved before. And we don't know yet what normal situations look like, what abnormal situations look like. These kinds of things tend to fail. And then there are a lot of research and science papers, as I mentioned, on IEEE Explorer, basically laying out how to manipulate these systems. And so that's something that we are then working with. And so the idea is basically what to do about this. And we, a couple of years, moved away from classic state estimation, where you, as I said, you have a model, you try to fit all the sensory information to the parameters of the model and try to minimize the error along that way. Since we need that model to base specific operational actions, decisions on that, we early on looked on how you estimate or determine and calculate certainty or remaining residual uncertainty in such a system. And one thing that we quickly stumbled upon is actually this notion of trust. For technical systems, interestingly, the German Research Foundation in the industrial applications has funded almost 20 years of research in trust assessment in industrial information systems. So basically, if you have systems, and the idea here is, especially in this industry 4.0 systems, where now specific production lines could span multiple countries, and you have something being automatically produced here, handing it over to another partner, and so on. So basically, you have a transaction with a lot of automated interfaces across multiple industrial information systems, and you need to get some notion of trust, since you, on the technical level, since you may not be really familiar with these systems, and these systems essentially are prone to the same kind of effects and incidents that I've talked about so far. And so the idea of trust is basically augmenting the classic output of a state estimation. And in this example, typically, if you do a state estimation on a power system, you get an active power value and a reactive power value. That is, the green one here would be the active power value, and the red one, the reactive power value. And what you now do is you collect a lot of contextual information on the states of the ICT devices that actually measure the voltage, measure the power. You get a lot of environmental information about the situations that they are actually installed in. You can collect environmental information that might be dynamic as well, since you have solar irradiation and stuff like that. You collect all the historic information that is available to these kinds of systems. And what you do is you augment these values with something that is called a trust model or trust value that is constructed out of trust facets. The classic model has 6 trust facets, and what they basically contribute to and try to estimate is basically do they adhere to their functional specifications? So you're not just measuring something, you are measuring, for example, the distance to the nominal values or to the expected values. You measure the utilization, for example, of a system that collects this data to assess the possibility that this may enter a state that could impose harm to that system, to the other system. So if you are running a sensor that is really, really hot in this example, that is something that then should be factored into account. You have the absence of possibilities to defect the system. That is typically looking at the historic data and the likelihood or basically the relevance of the information that these kinds of systems tend to fail often or have been hacked in the past. So you have a higher likelihood that this happens in the future. And other aspects that are technically, and the last two ones are more going in the direction of non-technical or more social aspects. For example, if you have this transition and you have encountered a new system that you're communicating with and that you're then reliant on. And if you encounter this for the first time and no one else you have ever encountered and are cooperating with knows about the system, is something different as something transient where you don't know it, but someone you trust actually knows the system. So there's a transient a transfer of trust in this aspect. And since we are talking about humans reacting to this, we also typically have this notion of, is that actually information available as a singular piece of information, or is there a lot of information going on and the tendency to overlook something in a specific scenario is actually pretty high. So those are then the things that you identify or collect to augment the classical values with. And the hypothesis that we of course have is that now all conceivable attack vectors, and you could also substitute attack vectors by phenomena or relevant phenomena, manifest themselves in a combination of impacted trust facets. So that's the hypothesis, of course, that we start with. But of course, you make the system estimate and the assessment now much more complex. So instead of 2 values, at one point now you get 2 values plus 6. And this at every point. And of course, the question is what to do with this very complex system. Is it even relevant what you're measuring as an outlier? I've just told you that we are seeing new effects and phenomena all the time because we are running the system completely in a completely new fashion. So it might be normal, it just might be unencountered so far. So we have to decide what to do with this and eventually maybe even do nothing. And an important question is actually, what is the worst that could happen given such a now much more complex state? And I will be coming back to this question in a few minutes. But just to give you an idea how we actually now do this, collecting a lot of contextual information on top of the things that we also already identify is something that, of course, requires a lot of data acquisition, requires a lot of pipelining. If you want to automatically in real time analyze this, also requires a mature and sophisticated information model. And what we did is we defined this so-called trust pyramid, and we instantiated this and we modeled this as so-called functional ontology. Basically, this is connected in terms of an information graph. Everything has a relation to each other, but you can actually read it as a pipeline going from bottom to the top. So you have something that is called the object of investigation. Those are the devices or the things or the processes that you monitor. You measure something, you have inputs, you have transformation functions that are decision functions, machine learning based forecasts, whatever. And those basically then lead up in this information processing ontology pipeline to the top. And what is actually really nice if you do it this way, that you get something that can, on the one hand, be instantiated in terms of a data stream management system, and on the other hand, can also be configured and analyzed with classic reasoning, since you have an ontology. And just to give you an example here, this is something that a student of mine did in 2019, and he got a best paper award from this. Basically, now every node could either be one of these transformation functions, which is connected through its inputs and outputs to upper layer transformation functions. This could actually also be a simulation model. And depending on what you're now measuring and the output that you're connecting in this functional topology, you could now actually do queries on this. You could, for example, connect a few devices, collect the information, and ask based on this model, what am I actually able now to analyze based on the quality and the number of the devices that I have? So you're asking about the potential outcome. And if you're not satisfied with this, you could add a few devices and so on to basically be able to assess, in this case, CO2 footprints or specific safety critical facets. But you can also use it from, in this case, it's tilted orthogonally 90 degrees from right to left. You can ask, if I now, you said you want to investigate something, give me the minimal set or the feasible set of input connectors and devices that I need to monitor to get a proper, in the context of quality, data quality, granularity, and so on, result that I actually want to do. It's a basic Sparkle query that you can now basically, poll on the system. And if you find something, you can immediately instantiate this. And this is really comfortable because you can now do this basically in real time online, which is something that you need to do because typically the energy system on the bottom is changing all the time due to weather conditions and so on and so forth. So the number of generators, actors, relevant actors change all the time. So that is really something that you are continuously asking and polling the system.
Yeah. Now you want to wait until the end.
If you want to ask now, you can briefly ask now.
Okay, I mean, just going back to the previous slide, you have a fairly complicated graph over there. How do you write?
I did not get the last word.
How do you know it's correct, that there are no mistakes?
Yeah, I don't know it exactly. What we do is we derive this from expert interviews and we model it as an ontology. What we by now actually can do, we have a scheme. So this is basically a meta model. And you can do, since it's a formal information model, you can at least validate the structure of the model based on the scheme that you derive for your ontology. But you actually, if you get bad quality information or bad input, you will eventually encounter it because, well, what you then eventually do is not getting you the results that you were expecting. But in that terms, we can prove or we can validate the format and the connecting and that the semantics of the model or the syntax of the model, but we have no means of validating this at this point.
Okay, thank you.
Yeah. And what we did now with this, we instantiated this, and this is just a very quick overview of our laboratory infrastructure where we have precisely this. We have a lot of endpoints. We connect this through multiple means, especially also simulating the communication layer on top of this, and eventually running a SCADA system, operating room system to actually manipulate these kinds of things. And what we did there is actually now focused on two things. And the first things that we actually did were connecting two of these domains, basically the power, the physical electrical power domain and the communication domain. So what we have here, we have these small embedded devices. One is like an embedded computer that you typically find in a substation, and this is a smart metering communication device. And so they typically measure a physical process. So they have a voltage, a current, maybe even a power input, and they also have a network connection, and you can do hardware monitoring on the device. So what we now do is basically we connect precisely then these additional aspects on this. So what we have here is we have a resource monitor looking at the RAM utilization, at the CPU utilization. We're looking at the network traffic that's going in and out of these devices. And we have a classic intrusion detection system looking for abnormal traffic. And what we now do is basically we integrate this with the classic state estimation path that's pretty much behind. This is not depicted here, but of course you would also now perform state estimation because these devices on the bottom measure voltage and current, and you get the state estimate, but now augmented with the utilization and the characteristics of the devices that actually measure these processes. And what we did here is, this is a depiction of how you would now see this in our SCADA room. So this is a classic SCADA view. We have the nodes and the edges are now the physical infrastructure. And you see on top of this is basically the communication infrastructure with the additional information from these two devices, from the hardware monitoring and the intrusion detection system. And what we did there was as a demonstrator in 22, I think, we also showed this at ENergy, is basically that you can now identify, or basically first depict, these 6 facets on top of each value. You could do this with these spider diagrams. And what you can now do is you can actually identify and replay these scenarios that are published under stealth attacks, where you typically see someone is hacking a field device to basically manipulate the measured value, voltage current, so that the SCADA system is unaware of something going on, or basically you are masking a critical situation. But now, since you're monitoring the device and see the added RAM utilization and CPU utilization, you get an intrusion system alert because someone's actually accessing this through the communication channel that is actually connecting that device. You can actually contextualize this and see a critical trust facet on top of this value that would otherwise not be detectable. And we've demonstrated this for a couple of these stealth scenarios and also published this in 23. To show that there are, well, now these undetectable scenarios that can now be detected. Of course, now you could probably design an attack that bypasses these kinds of calculations, but in the end, it's much more difficult to bypass such a system and go undetected in such a system that collects a lot of contextual information. And since we're not just looking for the intended anomalies, but also the anomalies that we get because we're connecting completely new systems and see completely new also physical behavior of the system, that is actually something that helps a lot with the network monitoring and control. And we have some prototypes to actually do this on top of classical SCADA views. Yeah. But let's get back to this question. So in the end, we started with a scenario or setup where you have a human operator in this control room actually having to decide or getting an answer that is really difficult and critical question: is what I'm seeing actually true, or is something going on that I have to react to? And of course, even though we now might be able to detect these kinds of things better than before, we are definitely not helping the human operator, because we have now presented him with an order of magnitude more information in the same frequency, maybe even a higher frequency that he had to deal with before. So the question still remains at every point in time, and now with this augmented scenario, what is the worst thing that could happen? And that's the second thing that I wanted to talk about today, something that we are now doing with machine learning based approach that we call adversarial resilience learning. And the idea is you have a model of your system, and in a reinforcement learning setup, you have 2 agents, which is basically learning agents. They actually have then neural networks to train, and one attacker agent tries, given the amount of information that the attacker has about the model and the flexibilities and degrees of freedom that the attacker is accessible to, tries to manipulate the system and typically tries to bring the system down. And the defender agent has, on the other side, typically better view, fuller view, more flexibilities to deal with transformer changes, shedding, switching on devices, changing topologies and stuff like that to actually mitigate this and stabilize the system. And what we do this in this reinforcement learning setup, we basically now run a lot of simulations on very fast computers. And of course, the shared environment, the digital twin of a CPS, is actually now a power system. And that is really fascinating. If you do this for a while, what you get on the one hand is a very sophisticated attacker that explores vulnerabilities and finds vulnerabilities. So basically, he tries to conquer the system, and in the end, you get a lot of attack vectors that can be used for testing the system, but also can be analyzed in order to repair the system. So if you find a vulnerability, the thing that you want to do is to close this vulnerability. More interestingly, on the other hand, is actually the defender, because now you get not just an agent that can eventually mitigate these attacker aspects or these attacker strategies, but is, if we stay with that question that I posed on the slide earlier, what is the worst thing that could happen? Actually, a function you could ask precisely this question. So in the end, you might get an oracle that you can ask. So I see an anomaly. An anomaly is always maybe an uncertainty about specific measurements, specific states. And under the assumption that this range of uncertainties actually could be under the control and be undetectable, usable by an attacker, we could now ask the defender, what is the worst thing that could happen? Do you have a strategy against this? If no, you have to react on this. If yes, we could actually assume the situation to be not critical enough to do something. So we train basically an oracle function. The nice thing is that, and I'm stepping away a bit now from this attacker defender or from the cybersecurity scenario, that in this training and this reinforcement learning, the attacker and defender also encounter these anomalies that do not come from intended malicious behavior, but more or less from loops that you, for example, introduce due to the connection of different sectors. You introduce feedback loops, you introduce oscillations and stuff like that. And that is, of course, something that is very helpful for us in order to identify the vulnerabilities and the aspects that we are interested in. There's, of course, an ethical dilemma. If we publish this, I'm skipping through this. Maybe we can discuss about this later. The nice thing is that now you can observe these games. And that's what we're doing for the last couple of years with ever more sophisticated scenarios. And typically you have a system performance. What we typically look at is the voltage in a specific branch. And this voltage needs to have a specific distance from its feasibility ranges. And so typically the attacker tries to destabilize the voltage, incur an overvoltage or an undervoltage with some specific devices under its control. The countermeasure then is, for example, the defender doing something at the transformer. Transformer is always very capable voltage controlling devices. Then the attacker might broaden its attack base, so introduce and use additional piece of equipment to yet again try one of these attacks, and the countermeasure then mitigates this eventually, and in this scenario, the defender would actually win. I have now two videos of early simulations where we could actually see these kinds of games running. And I checked to optimize the presentation for video mode. I hope that this works. So that is a very early, I think almost 4-year-old video that we had with a very basic network in the middle. These diagonal stripes is basically the amplitude of the voltage at the node. And you can see you have an attacker score and a defender score. And in this case, if I now trigger this, I hope you can see this. Things are going on. The attacker plays something, then the defender plays something. So they take rounds. And you can see based on the color gradient here, that sometimes the attacker has an advantage and sometimes the defender has an advantage. And that was actually very interesting because you could already now design dominant strategies, for example, in this game that include securing specific access to what we call defender nodes. That was, as I just mentioned, typically the transformer, because as long as you have control over your transformer, typically the defender has enough flexibility to countermeasure changes by the attacker on the devices that typically are then synchronized to introduce and excite these voltage instabilities. Since then, we have moved forward and introduced much more sophisticated and also realistic networks. This is actually a real world medium voltage network by a national network operator. And so we changed this, and you can already see that now the images here have changed a bit. What we have observed over the simulations is that typically the attacker tries to synchronize things. And synchronizing a lot of devices, being it the loading cycles of electric vehicles and so on, introduces massive spikes in voltage. So over voltage if you have feed in, under voltage if you draw a lot of energy. And this is something that is, or something like the go-to strategy for these attackers to try to destabilize the system. On the other hand, so you would see this if you now illustrate the parameter range as a color gradient, in this case, a gray gradient and now we have this grid of 9 devices, and each one is a variable, let's say generator, and the gray gradient basically gives you the set point. And synchronization means that this somehow starts to sync continuously and pump synchronously. Then we would see, okay, the attackers again found a synchronization attack, and we could actually abort this. Interestingly, this was not the case in this example. And on the right side, we actually have now a transformer or 2 transformers. This is why we only have 2 squares here. And the same thing is the tap changer is basically the transformer. And you can imagine the tap changer tapping up increases the voltage, tapping down decreases the voltage, but on a much larger scale with a much longer lever. And so typically you try to counter the synchronization with these tap changers. The thing is that this is the visualization of that simulation scenario. That's not what happened here, and still the attacker won. And that was something it took us, I don't know, at least 2 weeks to find out why. And the interesting thing is, since this was a real-world scenario, we actually used realistic transformer models that were delivered to us by the manufacturer of this transformer. And what we were not aware of, because maybe we did not read the manual diligently enough, that there was actually a maintenance log on the transformer. So basically the tap changer, the transformer, and since tapping the transformer is not done very often, after 1,000 switches, the tap changer would lock. And that would require an engineer to come to the field and unlock the system again. Interestingly enough, that was part of the model. So there was a basic counter that counted to 1,000 and then locked the transformer. And so what the attacker here learned was basically excite 1,000 switches and then do one synchronization attack that could not be mitigated by the transformer anymore. And of course, that's a very interesting attack, and basically for us shows the quality and basically the interesting, the capabilities of this approach. Since then, it became even more realistic. This is a network of Bremerhaven, a couple of kilometers north from here. And here actually we had a group of students doing a social hacking project where they basically invited themselves to the utility, have been invited because they were very smart students, and the utilities also wanted to hire a few of them. And they took a lot of pictures, asked for a lot of material, were able to model the system in our laboratory. And the presentation of that research group was basically inviting the utility and showing them all the vulnerabilities that this reinforcement learning agent model did actually find on their system. So that's still ongoing work. And really fascinating, because now you can, of course, also introduce communication models on top of that. Yeah, looking at the time, this brings me to the end. So that's what we are doing. And the key motivation, or that's part of the stuff that we are doing, it's obviously very fascinating. I at least get very fascinated by this approach. And the idea is that the classical systems tend to miss this. Well, you need this kind of multivariate impact analysis, or to us, it's very promising to find more of these vulnerabilities that will become or will be introduced into the system because you're running and operating the system differently from its intended design. Of course, you have now these IT cybersecurity attacks, which of course, need better measures. The thing is that this cat and mouse race, if you now introduce this R-based mechanism, trust assessment, smart attackers will find eventually ways around this. So there's basically this race condition. But the thing is that you might also, and this is a pretty new research perspective from us, might use this game theoretic approach to also come to a better design paradigm for designing these safety critical systems. So if you look how they are typically designed today, you have a risk. Basically due to events, phenomena, the classic earthquake, the classic tsunami, whatever, a strong wind incident, and you design a system not to withstand one of these things, but typically combinations of these kinds of effects. So you have basically the risk for many or n-fold of these failures and incidents happens at the same time, and this eventually degrades. Luckily, because the amount of investments and money you need to spend on a system to prepare it against the multitude of these effects is basically rising exponentially. And in the end, the decision that's typically been taken by the designers of the systems is identify the cutoff point where you say, okay, I'm preparing against this and this and this, and maybe a combination of these two, and maybe even of these three rare events, but the rest remaining risk is something I'm willing to take, and this is the cutoff point, so the acceptable residual risk, and that gives you basically the amount of money that you're willing to spend. The problem is, in IT security, the risk is not getting lower for follow-up or follow-up events and phenomena, but actually getting higher, because typically, especially in these hacking of the safety critical infrastructure, it starts with a completely automated botnet scanning your ports and finding something. If this works completely automatically, the second step is instantiated, trying to see what is actually accessible through that bad password, through that open port. And if there's something is found and you can reach something, then actually the automated attack is substituted or ramped up by additional resources, and then typically state-funded actors and so actually invest resources. And so the likelihood, if these first steps take place, for the third and the fourth step to happen, actually increase with the success of the preliminary or the step before that. And that means that actually the risk and the likelihood of follow-up events increase, and the risk is always the highest risk, the total blackout and loss of your system. And so in the end, you're missing that cutoff point. And yeah, that's interesting, because that also holds true with increasingly interconnected sectors and increasingly interconnected phenomena that you get from these systems. So the likelihood that you see a multitude of these failures happen and correlate with the interconnectiveness of your system. And so what we thought is, since we're already modeling as a game, maybe we can use game design aspects to derive design criteria from this. So if we cannot really design a system robust enough to keep this out, maybe we can design a system that has a dominant strategy for the defender. So basically, we would like to rig the game. We have a game that we want the defender always to win. Can we make it unfair for the attacker? If not, can we basically, since it's a game, design equilibria point such that the attacker may access the system, but with the mitigation of flexibilities available, he might not surpass a specific point. And so this is something that we are currently trying to model, trying to simulate, and getting our heads around. But this is something, I would say, yet another perspective that comes out of this research. Bottom line is, and I sometimes get asked from our partners, but everything basically started with introducing digitalization and IT to the system. So can we just not get rid of this anymore? And of course, there's no way back, because all the renewables, all the monitoring, and all the efficient utilization of the infrastructure that we have in place is only possible with this monitoring and optimization. And we just have to use the flexibilities and get this and keep this advantage. And that's something that we are doing. At OFFIS in Oldenburg, with this project that I reported from, and this is my last slide, I proudly used material from two of my postdocs, Michael and Eric here. And yeah, with that, I'm happy to answer questions now, later, whatever you want to know.
Thank you. Okay, questions? Anybody in the room? Yeah. Okay, so maybe, Sebastian, thanks so much for this talk. I think the first part is interesting, the second part was even more interesting and a bit scary. Could you comment a little bit about how the attacker and the defender networks are trained? I mean, so clearly you need a very accurate model of the system, but then you already said you have such a thing, but how do you train these? Is it just completely random actions with the reward function?
Yeah, honestly, we started with random actions on these very basic scenarios that I showed you in the first picture. So that was basically, if I remember correctly, an 8 or 10 node system connected to a ring. So it was actually really basic, and we only allowed modulating. I don't even think we actually modulated the power. I think we directly modulated the voltage. So that was super basic. To get a first feel for this game when you have a simulation of a power system in the middle. We gradually increased this, and honestly, we always reused the trained model from the model before. So basically, you could say it's a transfer learning approach. You get rid of a couple of layers of your network and then use the remaining system to train again. And we typically then broaden the parameters that are available to these agents to manipulate. And then it's still more or less a random approach. But as I mentioned, there are some dominant strategies that these attackers then learn. Synchronization is one. Of course, then we are typically dealing with, since there is to the attacker, that typically then exploits in this reinforcement learning setup, always all the time immediately the synchronization approach to well, get rid of that one or somehow change the reward function in a way that he not necessarily needs that sync attack, because we know it's there, and actually invest some resources in different strategies and explore some other strategies. But it's pretty much very incremental what we have done so far. We tried recently, I think we started the beginning of this year, there's some work on these stealth attacks, modeling this as attack execution graphs. So this kind of semantics looks like UML, where the attacks on infrastructure are modeled as an automaton. And basically, what we're currently trying to do is use this automaton as a base and then permutate and evolve these automatas, because that's something that has also been done for decades now. Use EAs to evolve automatas and get some strategies from this. But I think this is currently what we're doing on that.
The attack where you have these 1,000 switches and then they transform the locks, that could not be random, right? So you said there must be some information available to the attacker for that.
That's actually really interesting. Of course, we're doing a lot of simulations, and it's actually possible that this was the outcome of a completely random scenario, because we have a large cluster. We by now also have some of these NVIDIA clusters for training, and they do a lot of these simulations or these simulation runs to be trained. And I think at that point that was actually a random encounter of this lock, of this transformer tap lock. But that was really hard to find out in it, because we had no clue that it was in there.
Okay. And then from the defender's perspective, it seems to me that the defenders always have a lot, they have, it's a disadvantage, because the attacker can try all sorts of things, including coordination. The defender doesn't have control over the endpoint in the interior, right? Only the transformer attack points.
Yeah, one thing is actually that the defender has always one great card in its sleeve, and that's topology changes. Because so far, what the attacker does, as I mentioned, since the synchronization is the dominant strategy here for winning the game, synchronization is actually pretty sensitive to the network topology. So typically the attacker learns the best way to synchronize to overload the end of a very long line. And what the attacker can do is change topologies. If he sees that he's losing the game, changing topologies, which can be done. So that's at least on the medium voltage level. You can shift openings in lines, and that completely invalidates the dominant strategy of the attacker. if the attacker is not able to then immediately introduce the synchronization strategy for that change topology. So that is actually something that we also typically, when we get asked, okay, what can we do? I say, automate your topology switch, because in our simulation setups, this has been shown to be very effective.
Even randomly change normally open to normally close sort of periodically, every few hours, just to prevent the synchronization attacks from taking over.
Yeah. I mean, probably not periodically, but randomly. I mean, in Ethernet, if you see collisions, what you do is also you kind of randomly resend it after a while, and you could introduce these kinds of protocols also in this scenario. Of course, I'm always careful saying this is the silver bullet, because in the end, an attacker and attackers are always, you have to assume that the attacker will always be smarter than yourself, will find a way around this eventually. But yes, something like this. So a lot of these protocols that we come up with are actually inspired from communication protocols to mitigate congestions and blockage and these kinds of things.
I think you might be looking into, when randomized algorithms also have this notion of an attacker, right? And so the reason we do randomized algorithms is to prevent, since even the operator does not know what the next random configuration is, neither does the attacker. And so you always, this whole area of randomized algorithms is defined as a way to defend against the powerful attacker. And randomization, so what you're saying is absolutely correct. We can choose random time periods and random configurations. And this way, as long as your power balance is met, you should be able to mitigate against the transition attacks, because the attacker doesn't know the configuration is going to change. The spectrum is the same thing, right? It's
yeah, I can imagine. Yeah.
I really should bring this meeting to an end, though, because we have another group coming in. Let's thank Sebastian again. Thank you very much. Fascinating talk. Thank you.
Yeah, thank you. See you soon.
See you.